Welcome to the second lecture of the Microprocessor 8086. So today we'll discuss about the features of the 8086 processor and the register organization of 8086. So 8086 is being operated with 4.77 megahertz to 10 megahertz. With this 8086 simply it is operates 5 megahertz, whereas 8086-1 is being operated at 10 megahertz and 8086-2 is operated with 8 megahertz speed. So that is C. These are the three different versions available in 8086 processor: 8086, 8086-1 and 8086-2. So 8086 is operated 5 megahertz, exactly 4.77 megahertz is speed, and 8086-1 is 10 megahertz speed, 2 is so 8 megahertz speed. That is about the speed of the 8086 processor. So this 8086 processor is processing about 16-bit data at a time. So that is why it is called a 16-bit processor, and it is having 20-bit address bus. So with 20-bit address bus, it can support 1 MB of memory with 20-bit address bus. 1 MB of memory means 2 power 20 locations. So 8086 supports 2 power 20 locations, which is equal to 1 megabyte. Each location capacity is of a byte. So total 1 MB of memory it supports. And next is it supports 64K IO ports. So that is 64,000 IO devices. That means 8086 will support 16-bit IO address. 16-bit IO address. So with 16-bit IO address, 2 power 16 IO devices can be supported. So that is equal to 65,536 IO devices can be connected with 8086 processor. So that is 16-bit IO addressing. And totally 8086 is having 14 registers. Each register is of 16-bit size. So totally it has 14 registers. Out of this, 4 are general purpose registers and 4 are index and pointer registers and 4 are segment registers, and remaining 2, one is the instruction pointer and one is the flags register. So these are the total 14 registers present inside the 8086 processor. Then it has a multiplexed address and data bus. So 20-bit address and 16-bit data are multiplexed. That means 20-bit address, lower 16-bit address is used for both address part and data, and upper 4-bit address is used for status information. So multiplexing is used to avoid requirement of more number of pins. To reduce the pin count, so multiplexing technique is being implemented in 8086 processor. So it is data and address bus is multiplexed, because at any point of time processor, during the first T state, address will be sent by the processor, and during remaining T states of the machine cycle, processor can either send or receive the data part. So as a result, at any point of time, either data or address will be available on the bus. So both data and address are not available simultaneously. That is why address and data can be multiplexed together. Next, it has 6 byte queue. 8086 is having a 6 byte queue. So that is 6 bytes of instructions can be prefetched and stored in this queue in 8086. So at this point, with 8086 is 6 byte queue, whereas 8088 is having a 4 byte queue. So instruction queue size is 4 byte for 8088 and 6 byte for 8086. That is the difference between 8086 and 8088 processor. Remaining internal architecture is same for both 8086 and 8088. Only thing is interfacing with external I/O devices 8 bit for 8088 and 16 bit for 8086. So external interfacing with I/O device is the difference between 8086 and 8088, and instruction queue size is different 8086 and 8088. That is the difference. Otherwise remaining architecture part is same for both. Even pin count is same, and pin definitions are also same pin wise. So one can replace 8086 with 8088 without any problem. Then 8086 will be operated with single 5 volts power supply, and total 8086 is having 40 pins arranged in 2 lines, so 20 pins in each side. So dual inline package IC is the name given to this. And 8086 is operated in 2 modes, minimum mode and maximum mode. So in minimum mode, all the control signals required by the processor will be generated by the processor itself, whereas in the maximum mode, so the control signals will be generated by another device called bus controller on behalf of processor. So in maximum mode, generally multi-processor can be connected, multiple processors can be connected together. So multi-processor system can be implemented in the maximum mode, whereas minimum mode single processor system only can be implemented. So these are the different features of 8086. Next comes to the register organization. Already we talked about the previous slide that 8086 is having total 14 registers. So out of that, 4 general purpose registers, which are AX, BX, CX and DX. So these are the 4 general purpose registers: AX, BX and CX and DX. So the name itself is saying general purpose register. Any data can be stored in these registers. So we will discuss further details maybe in the next slide. So another 4 index and pointer registers. So they are source index, destination index, base pointer and stack pointer register. Okay, these are the 4 index and pointer registers used in the 8086. Then 4 segment registers: code segment, data segment, extra segment and stack segment. Apart from these 12, 2 more registers. One is the instruction pointer and another is flags register. So code segment register and instruction pointer together will give the address of the next instruction to be processed, and data segment and source index will give the address of the operand input, and extra segment and destination index will give the together the destination memory address for storing the results. The stack segment and stack pointer will give the address of the top of the stack. So base pointer can be used for pointing the offset address of any data area, whereas AX, BX, CX, DX are used for general purpose information storage. And the flags registry is used to store the status of the results and so control points of the processor controlling flags, and processor status flags will be stored in the flags register. So we will see the details in further slides. Okay, first is so general purpose registers. 4 general purpose registers are there. So they are AX, BX, CX and DX. So each general purpose register can be further divided into 2 8-bit registers, AH and AL. So BX is divided to as BH and BL. CX is divided as CH, CL. dx is divided as dh dl. Okay. So if we want to store 8-bit data, then we can use either AH or AL, BH or BL, CH or CL, DH or DL. So any 8-bit register can be used. Now these AH and AL are two 8-bit independent registers. So they are not depending on each. So AH is independent from AL and AL is independent from AH. So any 8-bit data can be stored in AL or AH. BH, BL, CH, CL, DH, DL. So these are the general purpose information. Any general data can be stored in this AX, BX, CX, DX. If it is a 16-bit data, it can be used AX, BX, CX, DX. Or if it is 8-bit data, either AH or AL, BH or BL, CH or CL, DH or DL. So that is a general requirement of these 4 registers. Apart from this general purpose, these general purpose registers can be used for some specific purpose. That specific purpose is, so AX can be used as a 16-bit accumulator. AX is used as 16-bit accumulator, whereas AL is being used as accumulator for 8-bit, whereas AX is used as accumulator for 16-bit operations. So for example, when you want to do the multiplication, when we want to perform the multiplication, so generally the multiplication is say MUL, say BH for example, then so multiplicand is in AX, multiplier is in BH. Okay, multiplicand is in AL, multiplier is in BH. So 8-bit into 8-bit multiplication, result 16-bit will be stored in AX. Okay, if I am using the multiplication application, so 8-bit multiplied with another 8-bit data, two 8-bit numbers can be multiplied, so result is 16-bit. So by default AX will be the default storage register for result of the multiplication. Okay, so if I want to use say multiply say BX, now the 16-bit multiplicand is in AX and multiplier is in BX. So once two 16-bit numbers are being multiplied, then result will be 32-bit. Then this 32-bit result will be stored in AX, lower 16 bits in AX register and upper 16 bits in DX register. So that is why even DX register special function is a multiplication. Okay. So for 8-bit multiplication only AX for the result, and for 16-bit multiplication, so AX will have lower 16-bit result and DX will have upper 16-bit results. So that is the special function of AX and DX for multiplication purpose. And another one is a divide operation. So even AX and DX both will be used for division operation. Suppose if I want to divide say BL, so division will be a 16-bit dividend will be divided with 8-bit divisor. So the 16-bit dividend will be in AX and 8-bit divisor is in BL in this example. So after division, the remainder and quotient. So quotient will be in AL and remainder is in AH. So whatever result we are going to get, so when we are dividing the 16-bit dividend with 8-bit divisor, then 8-bit quotient and 8-bit remainder. So 8-bit quotient is stored in AL and 8-bit remainder is stored in AH. Or if I want to use say divide, say for example BX, now the dividend will be 32-bit and so divisor is 16-bit. Now 32-bit dividend will be divided with 16-bit divisor. So where this 32-bit dividend is, so upper 16-bit of dividend will be by default in DX and lower 16-bit dividend is in AX. So DX and AX will be divided with BX then so we are going to get the result 16-bit quotient and 16-bit remainder. So the 16-bit quotient is stored in AX and 16-bit remainder is stored in DX. So that is how for multiplication and division applications both AX and DX are being used by default. So they are not being shown in the instruction. See, when we are using the multiplication, only the divisor address we are specifying to the register, whereas with the division the divisor address we are specifying to the register. For multiplication, so multiplier address is specified to the register, that is for multiplication and division. Next, other special operation is for IO. Okay, so this whatever data we want to send from processor to IO device or IO device to processor, so that will be through accumulator. Okay, suppose if we want to send data from the input device to processor, then we will be using in AL comma the address of the IO device. Okay, so IO address may be any 8-bit number, so 0 FF for example, maximum 16-bit address IO address. So now if we are using 8-bit address, so 0 to 255, that is 002 FFH. Okay, so 8-bit address can be used directly addressing mode, whereas if we want to use a 16-bit address, then so we have to use indirect addressing mode. In that case, DX will be used. For example, if I want to use the same instruction with the 16-bit in AL comma DX, before that move DX comma 16-bit address, so 16-bit address. Now DX is acting as a pointer for the IO device. So from 16-bit IO address, so from that IO device information will be transferred into accumulator. So this is how the DX is used as a special function for IO transfer. AL, AX, so AL accumulator is used for the IO transfer special function. So these are the special functions of AX and DX registers. Now the special function of BX register is acting as a pointer. So offset address is stored in BX register to point data area. So data area will be calculated, effective address or physical address of the data will be calculated. So with the base address and offset address. The base address is stored in the segment register and offset address is stored in one of the registers. It can be BX or it can be BP or it can be SI or DI or any other register. So as of that, so we can use BX as a pointer register for storing the offset address of either an instruction or a data. For both purpose it can be used. And CX is used as by default counter. If you want to perform a particular operation number of times, so that counting will be taken care by the counter. So by default CX will be used as a 16-bit counter and CL will be used as a 8-bit counter. So that is the role of the CX register, special function of the CX register. So these are the special functions of general purpose registers. They can be used for storing of the data as a general registers, or they can be used like this special functions. That is about the general purpose registers functionality. Next is index and pointer registers. So the index and pointer registers: stack pointer, base pointer, source index, destination index. Now if you want to use the top of the stack, so to point this top of the stack, the offset address of the stack area is stored in SP. So that means now, so what we can do is the top of the stack physical address is 10 in 10H into stack segment plus stack pointer content. So this total will give us the 20-bit stack address that will be pointing to the top of the stack. So for that, the stack pointer is used to store the offset address of the stack area. stack segment is used for the base address. And base pointer also similarly, so either you can be used for pointing the stack, one of the stack locations, or can be used for pointing the data also. Okay, that is base pointer register. Then source index, so to point out the input to data availability in the memory, this is used with this 10H into data segment plus source index will give the 20-bit address of memory where input data is available. Similarly, DI, destination index, so by default it is going to indicate the address of the result where the result is to be stored, address of the memory area where the result is to be stored. So for that 10H into extra segment plus DI. This is the default assignment, which will give the 20-bit address of the memory where a result can be stored. So like this, these pointer and index registers are being used for pointing the specific memory location, offset address of the memory locations along with the segment registers. So that is the role of index and pointer registers. Next, segment registers. So code segment, so this is going to point the beginning of the program area, data segment beginning of the data area, stack segment beginning of the stack area, extra segment another data area. So if the data area is more than, the data area needed more than 64 kilobytes, then so DS cannot be pointing to that. So DS can point up to 64 kilobytes of the data area. So additional data area can be pointed by this extra segment. So that is why a DS and DS are used for pointing the data area. So CS is for pointing the program area, SS is used as pointing for stack area. So that is why, so the address of the next instruction address is equal to 10H into code segment plus instruction pointer. That will give the 20-bit address of the next instruction. Okay, so code segment for program area, whereas data segment, so 10H into DS plus SI, 10H into ES plus DI. Okay, for stack area, 10H into SS plus SP. This is how these registers, segment registers and index and pointer registers are used for calculating the physical address, that is 20-bit memory address for either program or data or top of the stack. That is the purpose of these segment registers. And the 13th register is the instruction pointer. Already we talked about to point the program area. So 10H into CS plus so IP, the content of, so this IP is used for calculating the address of the next instruction, that is 10H into CS plus IP will give us the address of the next instruction. That is the purpose of instruction pointer, which is going to hold the address of the next instruction, of course offset address of the next instruction. Okay, so flags we will discuss in the next class. Thank you all.